I'll start recording that now, so I have a backup copy. All right, cool. So it looks like we got a few people here. Let's see. Let me make sure I got all set up. All right. Here we go. Um, let's see. Okay, so one thing we should start out with today that I didn't do last time that I forgot to. I always forget to. I always forget to introduce myself. My name is Bryce Christofferson. I got my PhD back in 2019 at UYO here in mathematics, and I taught for 6 years or so. Then I left to go to industry where I am still working, and I'm just teaching this class after work as a fun way to get back into teaching a little bit. And because I always wanted to teach complex and they needed someone to do it this year. So, cool stuff. We'll get into our lecture today, but I figured I would first start by saying that we've got the first homework posted since some people were asking about that. If you go to the assignments tab, you should be able to see it. Under homework number 1, it's right there. Due dates there. Due dates are also listed in assignments, as well as the syllabus tab, the in the syllabus itself, in the grade book, all that stuff. You can find it pretty much anywhere. Anywhere you look, it's everywhere. But yeah, so there we go. First homework assignment. It's short. I kept it nice and light, so nothing to stress everyone out right at the very beginning of everything. Just nice, simple 8 questions. Some of them have a few different parts, but it's all pretty straightforward. This course will start nice and light and then build up in difficulty relatively quickly. So I do encourage you to try to do well on these early assignments. I mean, once again, it is completion, or not completion so much as it is like to make sure you're keeping up with the reading and trying to actually do things as we go along. But in terms of your understanding, make sure to understand the basics that are easy to understand very well, because if you put that off, then once we get to the actually difficult material, it's going to be tough. So anyways, enough said about that. Let's get into the actual lecture here. Let's jump into it. So last time we talked a little bit about what we want to see, or what the motivation was for defining the complex numbers, and where we kind of come up with this basic idea of wanting to solve polynomial equations. So just here, I'll even start out with a little bit of extra stuff. Just a quick refresher. What we were doing is we were looking at various polynomial equations and looking at different sets of more and more numbers, starting with the naturals and building up to the integers. So we started with like 0, 1, 2, 3, so on, right? Oh, did I just... Okay, I just lost that. 1 second, guys. God damn it. All right. This will be an absolute beast if it doesn't come back, because I might lose those slides. This happened to me once before, and it was super annoying. Oh, thank God. Oh, I think I've got them. Okay. Ooh, that was a beast. Let's see. Let's see. Okay. So, tiny technical issue there aside. I think we're back on track. Moving a little bit towards where we want to be. Okay. Yeah. Anyways, here I'll skip since that took a little bit of our time right there. I'll skip a little bit of what we were going to talk about right there, and we'll just get a little bit more into the meat of it. So anyways, we started out looking at a variety of different polynomial equations over different sets of, some parts of the numbers you're used to working with, progressively more and more of them, and then asked ourselves when we could solve these uh, polynomial equations with the numbers we were looking at. And as we kept finding, we needed more numbers, and there's nothing special going on with C, the complex numbers, other than we just added another one so we can solve some more polynomial equations. The cool thing that ends up happening is that we're able to finally solve all of them. So before we go into any fancy stuff with that, let's just get a basic, no frills about it definition of complex numbers right here, and then we'll relate it to the more familiar instantiation of complex numbers that you've probably come across in algebra. So definition 1.1.1, the very start of everything. The system of complex numbers, which we'll denote with this cool blackboard C right here. This is just the set R squared. That is, just to be clear, these are just pairs x, y. Not getting a very good marker right there. 1 second. Let me get a little bit bigger there. There we go. These are just x, y pairs, regular old ordered pairs in the plane. R squared. So regular real numbers, 2 of them. So C is just, there are multiple ways to represent this, but this is ultimately what it boils down to. In terms of one of the easiest ways to think about it that doesn't require any extra fancy stuff. We just have R squared together with the usual rules of vector addition and scalar multiplication. So if you've taken linear, then that's where you'll, use that here. So namely, if you've got x1, x1, y1 plus x2, y2, then we're just going to add those component y's. That is, you'll get x1 plus x2, y1 plus y2. And if you take a scalar a, so some number a, real number a, and you multiply it by xy, then you'll get ax, ay. So just do it piece by piece. And I'm writing these guys as ordered pairs right here. Maybe some people are used to seeing vectors written like AB and like a square bracket, as opposed to pairs like this. And that's fair enough, but ultimately the same thing. You got 2 things and they're in an order. All right. So complex multiplication is the thing that differentiates this from just looking at R2 as a vector space. This is the point that's important for us, namely x1, y1 times x2, y2. We're going to define that to be x1, x2 minus y1, y2 in the first coordinate, and then x1, y2 plus y1, x2 in the second coordinate. So this seems weird at first. It's not really weird, especially if you're used to seeing things of the form z equals, let's say x plus iy, right? You might be used to seeing something like this for a complex number. And notice, really, what you've got is you've got the thing that's next to the I and the thing that is not next to the I. And is that really any different than having, 2 places in an ordered pair? No, it's really not. But let's just start right here, since we don't have to introduce any sort of fancy I's or anything like that, and keep it simple. So notice we can do something kind of cool here. So basically, just notice this. Under this rule of multiplication, what is 0, 1 times 0, 1? Well, x1, x2, so that's just 0 times 0, minus y1, y2, minus, so that's going to be those 2 guys, 1 times 1. Okay. And then x1, y2, so 0 times 1 plus y1, x2. That's 1 times 0. Hey, wait a second. What have we gotten? Well, look. 0 times 0 minus 1 times 1. That's going to be minus 1. And then over here we've got 0, of course. So we basically multiplied something by itself, and we got minus 1 in the first piece. This is really what you're used to when you see something like I squared equals minus 1 from algebra. Okay, so one way of representing this fancy thing is just to do pairs of numbers and have it work like this. You don't need to ask yourself, like, is I actually a number or anything fancy? Just take pairs of numbers and define multiplication to work like this. You don't have to do anything crazy. Just look at pairs of numbers. If you accept that pairs of numbers are about then you could define multiplication of pairs of numbers like this, and hey, we've recovered the property that we essentially want to have. So what we'll do is we'll now move to using this I notation kind of thing right here. And basically just think of everything like the usual XY plane. So we'll have pairs XY. Let's just put a dot right here and we'll say XY. Okay, XY is some point right there. And let me grab a different color. That means that X is going to be here, Y is going to be over there, usual stuff. And what we'll do is we'll think of this as the imaginary axis, im, and we'll think of this as the real axis right here. And then we can think of this point xy as something like x plus iy. And really, if you just think of I as being, 0, 1 like this, and then, you can even write it like, basically x plus iy, think of it like when you're dealing with vectors and you go like a like v1 plus b v2, right? If you have like a basis v1 v2 for R2, then these scalars are the coefficients for the basis right there, and you can write any vector in terms of these scalar multiples of the basis vectors. And that's really all we're doing right here. Just instead, we don't write anything next to the x part, and then the thing that's next to the in the y part, the imaginary piece, we actually bothered to denote which basis vector we're using. So it's just a little kind of light abuse of notation to make our lives a little bit easier. And everyone is already familiar, I am sure, at this point in your mathematical career with the idea of having a number system where I squared is -1. If you're not, please come talk to me at some point because we'll have some ground to cover. But basically just, straightforward idea. Most people have probably seen this before, and I don't think there's anything that's going to particularly surprise you. So we're going to just proceed like this, and we've got the property we want. Let's just take a second and think about some basic stuff that'll make us feel a little bit better about multiplying some complex numbers. Let's just do an example to start with. We don't want to take too long in any of this since the real meat of it will come a little bit. I mean, today's pretty easy in terms of what we're going to cover if you're used to this stuff. But it's always good to get a refresher. So let's just, for example, let's consider, let's calculate 2 plus, say, 3i times 1 minus 4i or something like that. Let's just go through and actually multiply this out. Okay, so 2 times 1, that's 2. 2 times minus 4i, that's going to be minus 8i. Okay, and then 3i times 1. This works exactly the same as when you're dealing with polynomials. That's 3i. And then 3i times minus 4i, that's going to be minus 12i squared. And then we just use the fact that I squared is -1. So we get 2 minus 8i plus 3i. And then when you square I, remember we get -1, so this will be plus 12. Okay, hopefully this is coming back to everybody, so we'll get 14 minus 5i. Okay, so 14 minus 5i. Nice, easy enough. Now, whenever we're dealing with all of our complex numbers, we're going to do a little bit of notation right here. We'll write, let's say this is some number z. Let's say that this is z, whatever that number is. Find z, where z is given by this, right? This piece right here, the 14, this is the real part of z, re-z. We'll just do the first 2 letters. And this is the imaginary part, im-z. So that's some notation we'll use. Occasionally we'll also be a little bit wild, and we won't use the parentheses. Yep. So to be clear here, I should be careful. Actually, I should. Let me be careful and write this very specifically so no one gets confused. It's the -5. That's the im part right there. So in this case, mz is -5 and real z is 14. So just think of these as the coefficients in the linear combination of basis vectors. Basically, when you have any complex number z, it's always going to be equal to the real part of z plus the imaginary part of z times I. This is the definition of how we're going to use real and imaginary right there, where real z and mz are always going to be real numbers. So just a little bit of notation, nothing too fancy. We'll just, do that. But anyways, moving on a little bit, just to kind of get a better vector space intuition, there's a good picture that we should kind of think of here. And I think that this is actually pretty helpful if you ever feel confused about complex numbers. I'm going to have to zoom out a tiny bit. Let's see. There we go. So if we want to think about, I've kind of drawn this a little bit before. We've got xy right here. Let's call that w. Then y would be the imaginary part of w, and x would be the real part of w. Then if we have some other complex numbers, some other point in R2, AB, let's call that z. So you've got z and w. Then, of course, this piece right here will be b. That's the imaginary part of z. And then down here we'll have, of course, a. That's the real part of z. Okay, good enough. And then if you add these guys together, just think of it as, here, let me put a different piece on there. If you've got this guy, right, put that in blue, and then put this guy in green. Notice that what we're doing is if I just kind of take this green guy and put it, the tail of it on the tip of the blue one, then I point up here, and if I put the blue one, the tail of it on the tip of the green one, then I would point right up here, and hey, wouldn't you know it, that's z plus w. So there's nothing too fancy going on right there. You're just going to add each axis's thing to get to the new point, and it works really nicely visually just by seeing this. And then when you put multiples like 2z, well, you're just going to stretch it twice as far. So you multiply a complex number by a real number, it's really just like scaling a vector. And then you add complex numbers together, well, you're just doing it component-wise. It's like vector addition, nothing fancy. The cool part is the multiplication. The multiplication is where you start to get a lot of the interesting concepts happening and a lot of the useful properties of complex numbers that make them something that we care about. So let's get into what those properties actually are. And this is where it gets fun for us. If you've taken an abstract algebra class, you may be familiar with the notion of a field. So, zoom in. Actually, let's see. So, there we go. That's enough. Okay, so fields are sets equipped with multiplication and addition, or really they're just equipped with two binary operations that satisfy a number of properties. We'll write one of those operations as addition. We'll write one of the other operations as multiplication. So one of them we'll just put by concatenation, the usual multiplication way. And the other way we'll just do it in the usual addition sense. Though it is not the case that for all fields you have to have addition. It doesn't really matter. We're doing complex numbers, so who cares? We're using addition in the regular sense. But here are the properties that you have to satisfy for a field. So z plus w has to be the same as w plus z for all w and z in your set. Okay, cool. This means that addition commutes. You can do it in whatever order you want. Z plus the quantity, w plus s, has to be the same as z plus w, that quantity, plus s. That is, we have to have a nice association property. It doesn't matter which order we do the pieces in. That is, if we do these two guys first, it doesn't matter compared to doing those two guys first. All right. There is a distinguished element called 0, some identity element such that z plus that thing is just z for all z's in the set. And then finally, there's a nice inverse element, which we'll denote by minus z, where z plus that element gives you the identity element, 0. Okay, cool. We're used to all of this from regular old real numbers. Good stuff. Multiplication, we have zw is wz. That is, the multiplication also commutes. zws, zw, that quantity, times s is the same as z times the quantity ws. That is, the multiplication is also associative. All right, so one piece and then the other piece. All right, good stuff. And then there's a special distinguished element in the set called, we'll call it 1. It's the multiplicative identity element. You do it to any other thing in there, so 1 times z, and you just get the same thing, z. All right, and then there's a special thing here, a special inverse element for every element. So z times z inverse, we'll call it, z to the minus 1, is the multiplicative identity element. And this holds for every z except for the additive identity, that special element where if you do the addition operation, it does nothing. Okay, so basically it's you've got, look, these 3 properties right here, between the two of them, are basically exactly the same, but with different operations. Okay, this final one is basically the same except for this this big caveat right here, where we say for z not equal to 0. So that's saying that we basically have the same thing, except that the second one, it plays nicely with the first one. Okay, good enough. And then finally, there's a distributive law that says that everything plays nicely together. This one is important, so it's so easy that you take it for granted, but z times w plus s is zw plus zs. So that is, you can carry it on through, piece by piece. Kind of drew that a little bit messy right there, and get things to distribute. You can distribute it across a quantity. Okay, across the addition. Nice. So those are the properties that you have to have any set equipped with 2 operations, denoted here by juxtaposition, concatenation, or addition, to get a field. And fun fact, would you believe it, Theorem 1.1.2, the first theorem of the class, the complex numbers, which we denote by this blackboard C, I'll write that like this, C forms a field. The complex numbers under usual addition and multiplication, whether we write it with i's or in the ultimately equivalent sense that we defined up here, you get a field. All right, cool. So having a field, this is a good thing to do, to have a field. What can we do? What's going to end up being nice here? Well, it's good that C forms a field. It means we at least don't lose any properties that we had from real numbers. After all of these things, the addition rules, multiplication rules, and distributive laws, are probably so familiar that you kind of can't even imagine something not having them. We've been doing this. This is basically what you teach kids in school. You teach kids in elementary school, in kindergarten, the field laws. You get really good at the field laws when you're in school. In particular, you get good with working with the reals. And luckily, nothing really changes too much with the complexes. You still have all of the nice field laws. The thing that's cool is you get extra stuff. Namely, and this is the big fact that we care about. This is proposition 1.1.3 in the text. So let Z be an element of the complexes. Just a little side note right here. When we write let Z and C, this little sign right here, this weird E looking thing, just means in. So if you pronounce it, we're saying let Z be an element of C, the complex numbers. We're saying let Z be a complex number. So this is just a fancy way of saying, suppose you have a complex number. All right, So we'll use this little in symbol, this weird E looking thing, kind of a lot. It just makes it easier to write statements down. But just in case anyone hadn't encountered that before, I thought it might be nice to mention. Um, so let me zoom in a teeny bit more here, make this easier to read. All right, proposition 1.1.3, let z be a complex number, then there exists a complex number w such that w squared is equal to z. This is nice. Namely, notice minus w will also satisfy this equation, but this is pretty important. So what does this mean? Well, w squared equals z always having a solution is what will allow us to say that every polynomial equation in C has a solution. Basically, any polynomial you write down, set it equal to 0, you'll be able to find the roots. All of them in C. That's cool. But let's just start out with the quadratics. We already know in the reals that every degree 1 polynomial, i.e. like ax plus b equals 0 or something like that, every degree 1 polynomial has all of its roots in R if its coefficients are in R. But we know that this is not necessarily true if we move to a degree 2 polynomial. And this is basically proposition 1.1.3, what we're going to use to be able to say that all of the degree 2 ones have roots. Okay, fair enough. So how do we show this? This is actually an interesting question, and it is kind of annoying to write, but we can get there. So, I don't know if, in the interest of time, we might go back at the end if we have enough time. But basically, here, I'll even pull up the textbook very briefly. Yeah, I have it right here. Okay, so the proof for 1.1.3, how it works is you just pick something. We'll say, let's let z be a plus bi. And then you want to find some w, which we'll write as x plus iy, such that, zoom out a tiny bit, such that z squared is w. Okay, so you solve it all out, and you'll get two things. You'll get x squared minus y squared is a, and 2xy is b. If you just graph these things, x squared minus y squared equals a, that's this weird hyperbola thing, and then 2xy equals b, well, that's just y equals b over 2x, and we know what the graph of multiples of 1 over x looks like. It looks like this, and then like that over there. And hey, we're trying to find the common solutions. Those are the points of intersection, and you'll get two of them right there. So if you go do a bunch of annoying symbolic manipulation, you'll get down to the actual answers, which are these big old ugly formulas right there. I don't think there's anything super enlightening about actually going through the nitty-gritty algebra of solving for those two ugly guys right there. But if we have time at the end, we'll do it. Basically, the point is just that we can do it, and if you want, you can actually write the formula down. It's not too bad. But that's in your textbook. I encourage you to go look at it if you want to. It's worth talking about. The more interesting things are calculating stuff like the square root of any given complex number, or some of the basic and important kind of simple stuff that you might want to get used to. This is not finding the W that does this is not a particularly interesting process. It's just tedious. Some of the things, though, that will be interesting to us, or at least not interesting, but maybe helpful at the very start, is doing some of the basic manipulations that will come up kind of a lot. So, for example, before we spend a bunch of time doing this, like I said, we'll go back to it at the end if we have enough time. Before we do that, there are a bunch of things that we might be interested in knowing. Namely, what about this z inverse guy right here? If we want to talk about z inverse right here, how do we actually compute what the heck that is? Namely, and I'll just get some extra space over here, give us some extra room to write. Namely, if I've got something like z equals x plus iy, what is Z inverse? If that's A plus IB, then what the heck what are A and B? How do we find these guys? Namely, how do we deal with inverses? This seems like it should be easy, but if you haven't actually sat down and done it and kind of thought about the trick to it, then it's kind of annoying. So let's actually just run through that really quick to get some intuition. This is a little bit more useful in terms of your everyday dealing with complex numbers sort of stuff. Namely, if you've got, say, like 1 over x plus iy, notice you can do this nice trick. This is the same as 1 over x plus iy times, well, we'll just do a clever form of 1. I'll do x minus iy times, or over x minus iy. That's just 1, so of course these are equal. Okay. Assuming that x and y aren't both 0, right? Okay. Well, then we just go through and multiply. Of course, we'll get x minus iy on the top, and on the bottom, I'll get x squared, and then I'll get minus, I'll just go through here very, very clearly, minus ixy plus ixy minus I squared y squared. Okay, so writing it all out in its full gory detail, I'll kind of bring that over a little bit so we don't run off the page. If we actually go through and do this, I'll get x minus iy over, and notice these two guys cancel out, and oh, minus I squared, well, I squared is minus 1, so minus I squared is just 1. So this is just going to be x squared plus y squared. And hey, wouldn't you know it, now we figured out how to write our complex number. Namely, we've got this nice formula right here. If you don't see it, we can just spread this out a little bit. We can just basically pull out a 1 over x squared plus y squared, and then have that like this. So if we've got z given by this guy right here, then this would be z inverse, right? 1 over z. All right. And now if we actually want to look at what that is, we can say, so the real part of z inverse is x over x squared plus y squared, and the imaginary part of z inverse is given by minus y over y squared plus, or x squared plus y squared. Bada boom. Okay, easy enough. So we can find inverses pretty straightforward. It's not necessarily the most intuitively simple to remember formula right there, but it is relatively natural, especially if you think about the fact that x squared plus y squared, well, going back up to this picture of C as a vector space, notice that the length of this vector right here, if this is x, right, and this is y over there, the length of this guy, which we will talk about this more in a moment, this guy's length is just the square root of x squared plus y squared. That's the length of it. So this 1 over x squared plus y squared is just the 1 over the squared length. Okay, fair enough. Notice it's not actually that bad. The inverse of x plus iy is x minus iy divided by its squared length. All right, fair enough. Pretty straightforward to see that. Now, if we want to do other stuff, is there anything else I want to talk about before we jump into some examples? Oh, yeah. There's one thing that bears mentioning. This is a slightly unrelated point to this piece right here, but it's a good question to ask before we just start doing computations. This is just a fun fact. We don't have, writing have in a very unfortunate way right there. Sorry. Still getting back in the swing of writing with this drawing tablet. We don't have less than or equal to or greater than or equal to in C. At least not in the same way. That is, unlike in the real numbers where I could say like 5 is like less than or equal to 10, it is not immediately clear how one would say this is good, but it's not really clear how one would say something like, I don't know, like 3i is less than or equal to 11 minus 7i, right? Does this even make sense? No, it doesn't. And it turns out that you kind of actually can't. It is actually totally impossible. There is no such ordering like the ones we're used to on C. So don't write, complex number greater than or smaller than another complex number, and don't expect the intuition of that to carry through. And the real reason for that is that while you can definitely imagine dealing with here, I'll just do a little bit of erasing, or actually, who even cares? While you can definitely imagine saying that like certain things are longer or shorter than each other in R2 like this, it is not particularly clear whether two things are bigger than or smaller than each other in some sort of a general sense. That is, while you're looking at a line, like the real axis right here, you can totally say which thing is further to the right or further to the left. But in a two-dimensional space, like C fundamentally is, it is not so clear which things are bigger or smaller. You could talk about just the length of the arrows and stuff, but then you're not going to have this nice property where the only thing that is less than or equal to something or greater than or equal to something is itself. That is, in the world of real numbers, we are all very used to saying things like if x is less than or equal to 5 and x is greater than or equal to 5, then x equals 5, right? You shouldn't expect the same kind of arguments to be possible in the world of complexes. And maybe I should erase those exclamation points because I don't want anyone to think that that's a factorial, right? But don't expect any of these arguments to hold in the same way in the world of complex numbers. So anyways, that small diversion aside, let's do a few examples and get kind of used to working with a few things. So we'll work through a few of them together right now. Let's start by, say, proving that 1 over I is minus I. Let's do that. 1 over I is minus I. Okay, so 1 over I, let's multiply that by a clever form of 1. We could do many different things, but let's just do minus I over minus I. Okay, in that case, then we'll get minus I over minus I squared, and then we'll get minus I over, well, minus 1 times I squared, which is minus 1, so there'll be minus I over 1, and so that's I, or minus I, sorry. 1 over I, the multiplicative inverse of 1 over I, or multiplicative inverse of I is negative I. Kind of cool. All right, fair enough. So that's kind of a useful fact. The multiplicative inverse of I is the additive inverse of I. Kind of works out well. Okay, let's do something a little bit trickier. Let's try 1 over I plus 1. Well, if we wanted to write this slightly differently, we could write this as 1 over 1 plus I, just to keep the i's always second right there. And we could multiply this by some clever form of negative 1. So let's do 1 minus I and 1 minus I. Clever form of 1. All right, multiply it out. 1 minus I on top. On the bottom, I'll have 1 minus I squared. And hey, wouldn't you know it, I can just simplify that down to 1 minus I over 1 plus 1. Oh, okay, so I have 1/2 minus 1/2 I, or 1 minus I over 2. Bada boom. Good to go. Good to go. Easy enough. Basically, it's like when we do like a rationalizing the denominator with like square roots and all that stuff. It's the exact same process. And we can use this to do other things. So say we've got, z plus 2 over z minus 1 for some complex number z. Let's just make our lives easy, and let's just say that z is equal to x plus iy. That way I don't have to write real z and mz for the real and imaginary parts. Let's start by saying let that be true. And in fact, realistically, I should take this and do that a little bit more explicitly, just to make our lives to be technically correct. Anyways. All right. Oh, it's the right size. Good. So let's say let that be that. Okay, so z plus 2 over z minus 1. Well, in this case, we can just write this out as x plus iy plus 2 over x plus iy minus 1. And if we go through and we combine things, then I can say that this is x plus 2, that's the real part, plus iy all over x minus 1 plus iy. Okay, good enough. I just took the real pieces and I put it together. Okay, and now I'll just do this fancy rationalizing. Basically, I'll just take x minus 1 right there, and I'll go minus iy over x minus 1 minus iy. And I'll multiply this whole thing by a clever form of 1. Bada boom. Let's just go through and actually do it together. So we'll get up top. This is where it starts to be a little bit annoying to write it out. X plus 2 times x minus 1. And then we'll go minus iy times x plus 2 plus iy times x minus 1. And then finally, I'll get minus I squared y squared. Good enough. And then on the very bottom, we'll just get x minus 1 squared. Notice it's just difference of squares. And then we'll go, I should write it out, I guess. Minus I squared y squared. And if we go through and we actually start simplifying things a little bit, notice we'll get a bunch of stuff on top and we can go through and run through that. But on the bottom, I'll just have x squared minus 2x plus 1. That's that piece right there. And then plus y squared. All right, cool. And then up top, I can multiply this out. I'll get x squared plus 2x minus x minus 2. And then all these things are going to have an iy on them. But notice over here, I'll get, well, minus I squared. That's just 1, right? And then we got the y squared right there. So that just turns into plus y squared. So I might as well throw it up here really quick just to keep it all in that first real chunk. And then I'll do all of these guys together. So I'll go plus iy, and then I'll carry this minus on into here, right? And I'll just go, all right, so I have minus x minus 2 plus x minus 1. Put it all together like that. And hey, would you know it, we've actually got our answer. This is just going to be, and I'll write it like this for easiness sake. This is 1 over x squared minus 2x plus 1, right? That's going to be in front of everything. And then we've got the real, we've got x squared, and then here I should just go through and do this, plus x minus 2 plus y squared. That's the first little chunk plus iy times, so we get this minus x and that x, they're going to get rid of each other. So I should write this here just as minus 3 iy. Okay, there we go. So good enough. We can figure out the real and imaginary parts just from looking at this. In particular, if we want to, here, I'll just write it like this. I'll just put everything all together, make it nice and easy to read. I'll just do x squared minus 2x plus 1 down here. And once again, I'll put it on the other part too. I'm just distributing this through so I can save myself some rewriting since this is tedious to write these guys out. And I'll even do this. I'll even put the I afterwards. Sorry for the confusion right here. X squared minus 2x plus 1, and then I'll put the I at the end of it. So what part is the real part? What part is the imaginary part? Well, that's not too bad. We just have this first chunk is the real part, and the second chunk is the imaginary part. Bum, 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 bum. Good to go. So if so this is the real chunk, and over here is the imaginary part, right? Okay, good to go. Nice. Any questions on that? I see we have a few people watching live. I don't want to be booking through this too fast. Any questions on how we got there? I know it's kind of annoying to write all of this out, but it's good to get some practice with it if you haven't done it in a little bit. No questions? All right, cool. Fair enough. Glad to see that everyone hopefully has done. It means everyone's keeping up and feeling very good about this material. It's great. So let's try solving the equation z to the fourth plus I is equal to 0. How could we do this? Well, obviously we're going to get that z to the fourth is equal to minus I, and so z will be equal to the fourth roots of minus I. Ooh, crap. What are the fourth roots of minus I? Well, intuitively, a degree 4 polynomial should have 4 zeros, right? How do I figure out what the fourth roots of minus I are? Well, that's a good question, and if you're watching live, I'll give you like a moment to scratch it out on your paper really quick, see if you feel comfortable about it. If you don't, then okay. But so okay, fine. If you've taken your time, then let's let z squared be equal to w. Then we'll have w squared equals minus I. So we have to find the square roots of minus I. Now, this is where the big annoying formula we were dealing with earlier, or we saw just a little bit ago, I kind of hinted at when we looked at proposition 1.1.3, this is where this guy would come in. So I will just very quickly write it down here and let you see what you should do. So we'll let write it like this. This is how your textbook does it. Alpha is going to be the square root of a plus a squared plus b squared's square root. Oh, sorry, I'm kind of being finicky on the pen right there. So let me get a big old square root. Okay. Over 2, and let's let beta be equal to minus a plus the square root of a squared plus b squared over 2, and we'll put all of this into a big old square root. So the difference here is whether you have the a or the minus a. Then if we're looking at w squared equals z, where oh, I should be clear about what a and b are. Sorry about that if I'm being confusing. So here, where z is equal to a plus bi, and here I'll even just leave it like that. If we've got this, then we can write w as plus or minus. Sorry, 1 second here. And this is where it's annoying to write it out. It's alpha plus mu beta I, where mu equals 1 if b is greater than or equal to 0, and mu equals minus 1 if b is less than 0. Okay, so look, that's not super intuitive of a formula, but we'll get a better way to do this next week, and that's why I don't love to see it look like this. But if we're, say, like for this question, looking at for the square root of minus I, w squared is minus I. Well, in that case, if we're saying w squared is minus I, then we're saying, here, let me use a different color now. So that would be 0 plus minus 1i, right? So b is minus 1 in this case. So mu will be minus 1 right there. That means we're in this situation. And our roots will be omega is equal to plus or minus. Well, we should do the alpha part. So it's going to be 0 plus 0 squared plus b squared. So that's plus minus 1 squared. So it's going to be 0 plus the square root of 1 squared. So it's going to be 1 on top over 2. So it's square root of 1/2, right? So square root of 1/2. That's the first little chunk right there. I should put a big parenthesis. That's the alpha. And then mu will be minus 1. So minus, and then beta, well, that'll be minus 0. Oh, look, because the only difference is this minus a versus a positive a, we're just going to get minus 1, minus root 1/2 I. Okay, so there we go. There's our two pieces right there, right? Omega will be that. Let's bring that on over here. So, not omega, w, sorry. So omega w is plus or minus square root 1/2 minus square root 1/2 I. Okay, and that's just 1 over root 2 if you like. But either way, however you feel like writing it, whether you want to rationalize the denominator or not, doesn't really matter. Or, yeah, root 2 over 2, whatever you feel like. But let's leave it like that. So that's what we get for w right there. Now, if we want to actually go through and solve the rest of it, well, then we just have two other equations we solve for. Namely, we just go through and we solve for each one of these, and we get it yet again, right? So we take this guy right here. Here, I'll make this slightly easier. I'm just going to write it like this to make it simpler for us to deal with. Oops. That's a little bit more legible to write it as 1 over root 2. And so each of these gives us something. So since z squared is w, we'll have two equations. We'll have z squared equals the positive 1 over root 2, minus 1 over root 2i, and then the negative 1, which is z squared equals minus 1 over root 2 plus 1 over root 2i. And notice we just take each of these guys and we repeat the process. That's all you have to do. And in the interest of time, since we were pretty near the end of it, or actually probably almost at it, actually we're probably slightly over. I forget that this only goes for 50 minutes. What you'll ultimately get is you'll get z is equal to, well, here, you should do it. You should do it to see what you get. You just repeat the process we did for the w right here with each one of these, and you'll get yet another pair of answers for each of them, and like expected, you'll get 4 answers. What those are, if you want to actually see, you can find on page, let me pull it up right here. Page 9 in your textbook, they work through the same example. All right, fair enough. So that's the annoying business of calculating these roots. I really don't think that you probably want to deal with this. We will find a much better way to write this later on. In fact, in our next lecture, we'll probably get to it. If not, the next one, the one after. But there's a much better way to do this. But for now, you should do it like this. You should go through and use these dastardly formulas that are very annoying to work with, and actually get some intuition for why it is cool we have better ways to do things. But that is how you would solve something of this nature. I had another example that I wanted to do. This is obvious. So for complex numbers Z and W, if you it is worth sitting down and actually proving that the real part of a sum is the sum of the real parts, and the imaginary part of a sum is the sum of the imaginary parts. It seems so obvious and simple, but if you're new to dealing with proofs, like maybe some people in this class are, you should actually sit down and try it. It'll make you feel more comfortable. And then if you, on the homework, have to prove things about, say, like the real part of a product or the imaginary part of a product or something like that, it won't be so strange. But for right now, I think, actually, since it is 6:50 or 5:50, 6:58, yeah. I'm in a different time zone than you guys, by the way. So if I say the wrong time, I apologize. It's 6:58 my time, meaning that it is 7:58 your time. So I should probably call it quits and let you guys go enjoy your Friday night. Um, Thank you for joining the stream, those of you who attended live, and those of you who are watching this later. Right on. I totally understand. If you have any questions, please shoot me an email, and we'll work on it from there. The homework is up. We'll take it from the top next week. Have a good weekend, and if you've got any questions, I'll sit around for a minute here. Oh, there we go. All right, no one's saying anything, so I guess that's the end of class. I'll see you guys next week. I hope you have an awesome weekend, and yeah, peace out.